Today's industrial complexes are as varied in design as they are in function. When we take a closer look at control elements, however, similarities between industrial plants become more evident. In this program, we'll examine one control element that can be found in virtually every industry, the control valve. The control valve is the most widely used final control element. Control valves manipulate flow in order to control such variables as pressure, temperature, and level. Control valves exist in an almost limitless number of forms, sizes, and materials. It's easy to understand why, given the immense variety of control applications present in the modern industrial world. But even with all these applications, tasks performed by any control valve fall into three general categories: dispensing, dissipating, and distributing. In each of these categories, the control valve is involved with the disposition of process energy. Because cost effectiveness and energy conservation are so closely linked, and as costs continue to increase, it's important to know how the control valve contributes to efficient and precise control. In a dispensing application, a control valve is used to dispense a utility, such as water, steam, or gas, to a process. This drawing shows a simplified example of such an application. Here, the control valve regulates the amount of cooling water provided to the process. Note that energy has been expended to make this water available to the process, and a control valve is being used to dispense it. When used in a dissipating application, control valves provide a pressure letdown capability or pressure dissipation. This drawing illustrates an application in which pressure is dissipated. The fluid in tank A is processed at high pressure. During processing, pressure tends to rise. Excess pressure is relieved to another step in the process. The control valve in this process provides the pressure letdown service. Energy, in the form of pressure, is dissipated by the control valve. Finally, a distributing application is one in which a control valve must divide a process stream. Let's look at this drawing as an example. In this application, two tanks receive fluid from a process stream. Control valves are used to properly distribute flow to each of the tanks. You can see that in this type of application, energy in the process is distributed by the control valves. Now, all control valve applications include at least one of these functions, and in many cases more. For example, in a distribution application, pressure may also be dissipated by the control valve. It's clear that the performance of a control valve can have an effect on the amount of energy consumed by the process, so it's important to select the proper control valve for each application. What are some of the other reasons? Let's take another look at this system. Suppose the quantity of the product in this process stream is temperature dependent. If the control valve does not have the proper flow control characteristics, process temperature will not be properly maintained, and as a result, product quality will suffer. In today's marketplace, this can be very costly. Another reason it's important to have the proper control valve installed is the cost of maintenance. An improperly sized valve will require maintenance more frequently than a valve that's been properly sized and selected. In addition to requiring more frequent maintenance, an improperly selected valve is much more likely to cause unscheduled process downtime due to malfunction or failure. As you may know, the costs associated with such a failure can be astronomical. But there can be much more involved than the normal operation and costs of business. An improperly selected valve can have an adverse effect on the working environment in your plant. Excessive valve noise is one example. Valve noise can be the result of mechanical vibration, cavitation, or aerodynamic vibration. Studies have shown that excessive noise contributes not only to hearing impairment, but to other physical problems as well. As a result, limits on the exposure to noise have been established and must be considered when selecting the control valve for an application. You also need to consider the potential for environmental contamination in the event of a valve failure. When you weigh the costs of cleaning up pollutants, paying fines, and of a negative public image, the cost of properly selecting a control valve is insignificant. Of course, the most important consideration is the safety of human life. Can a valve failure create a hazardous situation or result in personnel exposure to a dangerous process fluid or possibly an explosion? These are the kinds of questions you must ask yourself when sizing and selecting a control valve. In many systems, a control valve may be subjected to more severe conditions of temperature, pressure, corrosion, and contamination than other process equipment, yet it must perform satisfactorily with a minimum amount of attention as it manipulates the flow of process fluid. This program will help provide you with some of the information you need to make the proper decisions when sizing and selecting a control valve. Additional material on these topics can be found in your text. Stop the tape now. In the last segment, we discussed 3 general categories of control valve tasks. In this segment, we'll start by looking at functions that control valves must perform in each of these process operations. It's important to understand these functions because they each result in different requirements on the design of a control valve. When used in a continuous process such as this, the function of the control valve is to modulate the flow of the process fluid. So, for a control valve in this type of application, flow characteristics are a primary concern. You should also note that control valve position is dictated by an external controlling device, such as this digital controller. Safety relief valves and other self-contained regulators are not normally considered to be control valves. When a control valve is used in a batch process, its primary function may not be modulating fluid flow. It's common in a batch process to use a control valve to start and stop the flow of a fluid, particularly when a precise volume of a fluid is being measured. In this situation, the shut-off capability of the valve may be a more significant design consideration than it was in a continuous process. In another application, quick opening or closing may be the primary concern. This is the case when the control action is taken to prevent an undesirable event from occurring. An example might be one in which a flow path is opened in order to relieve high pressure. So you can see different control applications require different control valve designs. Similarly, different control valve designs may require different types of actuators and positioners. As you may know, an actuator supplies the necessary force to operate the valve. This drawing illustrates one of the most common control valve actuator combinations, a single-seated globe valve with diaphragm actuator. The actuator needs to overcome several forces to properly position the valve plug. It must overcome fluid forces exerted on the plug, it must overcome spring forces, and it must overcome resistance to movement caused by friction. Of course, different valve designs may place different requirements on the actuator design. For example, with this type of valve, the actuator must additionally supply the force needed to distort the diaphragm seat to provide a tight seal. As you might imagine, the forces acting on a rotary valve, such as this butterfly valve, are much different. Because of the rotary valve design, the actuator mechanism must be of a different design. Another component used in conjunction with a valve actuator is a control valve positioner. A valve positioner is a device which precisely positions the control valve plug and stem in response to the control signal. A valve positioner acts as a feedback controller whose set point is the incoming control signal and whose controlled variable is the position of the valve stem. Let's take a look at how the positioner ties into a control system. We'll start by looking at a control valve without a valve positioner. This valve receives a 0 to 20-pound air signal from the controller. The air signal is opposed by a spring that has a range of 3 to 15 pounds. Thus, valve position is directly controlled by the output of the controller. When a positioner is used, it is included in the loop here. It receives the output signal from the controller. This signal is used as the positioner set point. The positioner compares the actual valve position to its set point, and if the valve stem is incorrectly positioned, the positioner will either add or exhaust air from the actuator, as required, until the correct valve position is obtained. Positioners are usually high-gain proportional controllers. When the primary loop is slow responding, they can be used to compensate for local disturbances and non-linearities before their effect is felt by the primary controller. Under certain conditions, a positioner can improve the speed of response of the primary loop by matching the ranges of the controller and the valve actuator. Generally, valve stem positioners are linear. That is, they change valve stem position linearly with respect to controller output pressure, as shown by this chart. Some positioners are provided with a means, generally a cam, to change this relationship. Effectively, this creates a different control valve flow characteristic. In the next segment, we'll begin to look at valve and actuator designs. Stop the tape now. Up to this point, we've been discussing the basic functions that control valves perform and how the specific application can affect the design requirements for a control valve. Now it's time to look at the various valve designs available. As mentioned before, control valves are available in an almost limitless number of forms, sizes, and materials. However, their action generally falls within two categories: linear motion and rotary motion. We'll start by looking at some linear motion control valves. The most common control valves are globe valves like this one. Let's take a look inside. This design is called a single-seated globe valve. These valves are often used in smaller sizes only. That's because the differential pressure across the valve plug causes an unbalanced force to act on the valve stem. Double-seated globe valves can be used to reduce unbalanced forces. In this type of valve, the force from differential pressure applied to the valve stem acts on both valve plugs in opposite directions. The force tends to cancel out, thus reducing the required actuator size. Now, these forces do not entirely cancel each other out. One reason is that the two plugs are slightly different in size to allow withdrawal of the smaller plug through the larger port for maintenance. You should also be aware that these valves may not seat as tightly as single-seated valves. As you can imagine, it's nearly impossible to close both ports simultaneously, especially when thermal expansion has affected the valve construction materials. Three-way valves are simply a design extension of double-seated globe valves. This three-way valve is designed for use as a diverting valve. When the valve is in an intermediate position, fluid flow is divided between the two ports. When the valve moves to this position, the majority of the fluid is diverted through the upper port. And when it's in this position, the majority of the fluid flow is diverted through the lower port. Similar valves have been designed for use in applications where two streams converge into one. Another type of globe valve is the angle globe valve. The inlet and outlet of this type of valve are at right angles to each other. These valves are often used where piping layout does not allow the installation of an inline globe valve. They're also useful for dealing with erosive fluids and abrasive materials. In these applications, flow through the valve in this direction, that is, flow tending to shut the valve, minimizes erosion of the valve body. However, there are some problems that can occur when using this valve. Turbulence created by the valve in downstream piping can lead to severe pipe vibration and noise problems. Additionally, when the pressure drop across the valve is relatively small, severe cavitation may occur. Factors such as these must be kept in mind when selecting a valve. Your text provides information concerning additional types of globe valves. Now, while globe valves are the most common type of valve, there are a number of other valve types used in industry. Gate valves such as this are widely used for on-off service. The throttling characteristics of these valves are generally very poor, and use in a throttling application can cause rapid valve wear. As a result, gate valves are rarely used to modulate flow. However, a few designs have been adapted to provide good throttling service. This design is called a multi-orifice gate valve. The valve closure consists of a fixed plate and a moving plate. Flow is controlled by changing the alignment of long, narrow orifices in the two members. These valves provide good control characteristics for gas, liquid, and steam services. Another adaptation of the basic gate valve is the V-orifice gate. The V-shaped orifice characterizes flow capacity through the valve with gate position. In many instances, the gate is a thin plate with a sharp knife edge. Knife-edge gates are often used to shear through the flow of solid materials, such as powders or granular substances. Other difficult fluids have led to the development of other valve styles. Diaphragm valves are well suited to applications dealing with corrosive liquids and slurries. A flexible diaphragm provides for valve closure. However, limitations of the diaphragm material may restrict their use to low-pressure, low-temperature service. When diaphragm valves are used with hazardous materials, the valve should be specified with a special bonnet, one that has a packing box. This will serve as a backup in the event of a diaphragm failure. Pinch valves like this and clamp valves are similar in nature to diaphragm valves. Throttling is provided by squeezing and distorting a hose or tube. Notice in this valve that the actuator is attached to the tube wall. This construction allows the valve to operate in a vacuum service. Other designs rely on process pressure to reopen the tube. These valves are well suited for use with corrosive slurries and are available with liners rated to 350 degrees or more. As with diaphragm valves, they're available with a packing box to minimize leakage in the event of a tube failure. In the next segment, we'll discuss rotary motion control valves. For now, stop the tape. All the control valves we've covered so far have been linear motion valves. Now it's time to look at some of the common rotary motion valves. The butterfly valve is one of the most common rotary motion control valves. Inside, these valves have a rotating vane that provides the valve closure. These valves offer simplicity and low cost, as well as good flow control characteristics. Also, as a result of the rotary motion of the stem, the packing boxes can be of a relatively simple design. That's because one factor that causes corrosion of the valve stem in a linear valve has been removed. That is, the alternate wetting and drying of the valve stem as the valve operates. There are many variations in the design of butterfly valves. Each different style of valve body, vane, or seal is designed to provide some unique feature or capability. A wafer body allows the valve to fit between piping flanges like a sandwich. A seal ring may be provided in order to obtain leak-tight sealing. Disc and stem orientation may vary as well, usually to obtain a better torque relationship with the actuator. As with any valve, there are problems you need to be aware of when making a selection. Because of its design, cavitation is more likely to occur in a butterfly valve than with some other valve designs. And because it is fast-acting, there is the possibility of damage due to water hammer when used in a liquid service. Another common rotary valve is the ball valve. Originally used as a tight shutoff valve, advancements in materials and design have made it suitable for use as a modulating device. The flow closure member is a sphere, in this case a full ball, that has an internal passageway. Rotating the ball regulates flow through the passageway. This particular design is called a floating ball. This is a drawing of a full floating ball valve. The seat rings provide all of the support for the valve. When the valve closes, upstream pressure assists in forcing the ball against the downstream seat. However, to permit this, some backlash must exist between the ball and the actuator. The result is hysteresis, or a deadband, which can degrade the quality of control. In a trunnion-mounted ball valve, the ball is supported and secured by stub shafts. In addition to eliminating the deadband that may exist in a floating ball valve, a trunnion-mounted ball valve requires less torque to actuate when exposed to high differential pressure. A tight seal is provided by the upstream seal ring, which is forced against the ball by upstream pressure. In some designs, this sealing force may be assisted by a spring. There are a number of other variations of the full ball valve. For example, a full bore ball valve can be used where service conditions require that lines be pigged or rotted out. Three-way ball valves have a flow passage that makes a turn within the ball. These can be used on converging and diverging streams. Four-way valves also exist. Segmented or characterized ball valves utilize a segment of a ball which is supported by stub shafts. The leading edge of the ball and the inlet port are specially shaped to achieve a different flow characteristic. Ball valves offer the highest flow capacity of many commonly used control valves. They're especially useful for pulp and slurry applications because of the tendencies for these materials to settle or strain. However, like the butterfly valve, a ball valve is more subject to cavitation in some applications than a globe valve. Similar to a ball valve in some respects is the plug valve. It's the simplest of the rotary valves. These valves are closed by rotating a plug that has a port in it. The plug can be cylindrical, as shown here, conical, or spherical in nature. Additionally, the port may be characterized to provide a desired flow characteristic. This eccentrically rotating spherical plug valve provides for a modified linear flow characteristic, as well as a tight shutoff and easy operation. Valves such as these are widely used for handling viscous liquids and slurries. We've covered a number of common valve types in this segment. In the next segment, we'll look at some of the more typical valve actuators. For now, stop the tape. There is a great deal of diversity in the types and styles of control valve actuators available, each having some special advantage. In this segment, we're going to discuss some of the types of actuators, how they work, and what their advantages are. We'll start with a very common type of actuator, the pneumatically operated actuator. It's been estimated that more than 90% of all actuators used on industrial control valves are pneumatic. With that in mind, let's look at this simplified drawing of a direct-acting diaphragm actuator. The diaphragm is located here, between two casings. To ensure good strength and flexibility, diaphragms are generally molded from a fabric-reinforced elastomer, although other materials are available for special applications. Two forces act on the diaphragm to properly control actuator stem position: force from actuating air pressure above the diaphragm and force from the actuator or range spring below the diaphragm. Increasing the air pressure will result in a downward motion of the actuator stem, while decreasing the air pressure will result in an upward motion of the actuator stem. This relationship between air pressure and stem position can be reversed by using a reverse-acting diaphragm actuator. In this actuator type, actuating air pressure is applied to the lower chamber and the upper chamber is vented. The spring mounting arrangement has been altered so that upward motion of the stem, caused by increasing pressure, will cause the spring to compress. These types of actuators have a number of advantages, including their adaptability to a wide variety of valve sizes and applications, their low cost, and their high performance. However, these actuators do have limitations. There are limitations on the length of valve stroke that can be obtained, and there are limitations on the amount of force that can be developed with a flexible diaphragm actuator. One type of actuator that has been developed to overcome these limitations is the piston actuator. A piston actuator can easily be designed to provide a long stroke and to operate at high pressures. Because piston actuators can operate at higher pressures than diaphragm actuators, they can deliver more force to the valve stem and plug. Since a controlled air signal is typically only 3 to 15 psig, positioners are used in conjunction with piston actuators to provide air at higher pressure to the piston. Looking at this drawing, you can see that the actuator is simply a piston that slides within a cylinder. A seal is provided between the piston and cylinder by piston rings. This seal, which may be as simple as an O-ring, adds to the force the actuator must overcome when positioning the valve. As with a diaphragm actuator, there are opposing forces acting on the piston that are controlled to obtain the desired positioning. In a direct-acting piston, actuating air applies force in this direction. The opposing force is often provided by a fixed or static air pressure that acts as an air spring. There are some designs in which the pressure on both sides of the piston is varied to control valve position. These actuators are said to be double-acting, and they require the use of a four-way positioner. Of course, there are reverse-acting designs as well. For now, though, let's look at the pneumatic arrangement for a direct-acting piston-actuated control valve that uses an air spring. In this system, a pressure of 20 psig is maintained on the bottom of the piston by this regulator, regardless of valve position. Now, for installations like this, consideration must be given to the fact that an air system failure may occur. In the event of such a failure, this actuator provides no fail-safe action. To provide fail-safe action, a check valve may be used to block air spring pressure. Another approach is to use an actuator design that includes a helper spring. Other solutions may include the use of an air accumulator or capacity tank to provide an air source for fail-safe positioning of the valve. Another consideration is the breakaway friction associated with the piston rings. Overcoming this friction adds to the hysteresis in the control system. A rolling diaphragm actuator has a design that offers much lower friction than a piston actuator, but still has the capability to provide a long stroke and to operate at high pressure. The actuator consists of a piston that is sealed with a rolling elastomeric sleeve or diaphragm. Actuating air pressure is opposed by a spring. Increasing air pressure results in a downward motion of the actuator stem, while decreasing air pressure results in an upward motion of the stem. As with other diaphragm actuators, the diaphragm material may not be suitable for use in all applications. Factors like this must be kept in mind when selecting an actuator. Now, so far, we've been discussing pneumatically powered actuators. However, there are circumstances where a different type of actuator would be more desirable. For example, a long distance to the control valve may result in unacceptable pneumatic signal transmission delays, or it may not be practical to provide a pneumatic signal to a remote location. One type of actuator that is not affected by these factors is an electromechanical actuator. Essentially, these devices have an electric motor and gear train that actuates the valve. The gear train drives a worm gear, which converts the rotary motion of the gears to linear motion for the valve stem. The magnitude of the control signal sent to the valve corresponds to the desired valve stem position. An electronic positioner compares the input signal to a signal that corresponds to actual valve stem position. The signal corresponding to actual valve stem position is provided by either a potentiometer or a linear differential transformer. If there is a difference between the two signals, the positioner provides the required voltage to actuate the motor. When the error is corrected, output voltage to the motor is returned to zero. A major disadvantage of some electromechanical actuators is their inability to move to a fail-safe position in the event of a power failure. And these actuators are relatively expensive. Another actuator with similar characteristics is the electro-hydraulic actuator. These are completely self-contained units, requiring only electrical power and a control signal to operate a valve. Electrical power is required by the actuator to operate the integral hydraulic pump. A servo valve controls the flow of hydraulic fluid to both sides of a double-acting piston. Basically, the servo valve acts as a positioner to adjust the two flows based on the input control signal and on feedback from actual stem position. One problem with these actuators is that the cost remains relatively high when compared to diaphragm actuators. Additionally, because the actuator requires a constant source of hydraulic pressure, there is a constant use of electricity to operate the pump. Of course, if there is an external source of hydraulic power readily available, then a hydraulic actuator may be used instead. As you can see, it's very similar to an electro-hydraulic unit. The major difference is that hydraulic power is supplied by an external source. This permits extremely high actuating force to be developed. Now, you may have noticed that all of the actuators we've looked at so far are for linear motion valves. However, there are many control valves that require rotary motion. Motion transfer mechanisms are devices placed between a linear actuator and a rotary valve that function to convert linear motion to rotary motion. A lever, such as this, or a rack and pinion, can be used with both piston and diaphragm actuators. You can see that linear motion from the actuator causes a rotary motion in the valve stem. These devices are usually limited to 90 degrees of rotation. One type of actuator that is designed to provide rotary motion is the vane-type actuator. You can see that a vane is enclosed in a casing the shape of a pie. This end of the vane connects to the valve stem and acts as a pivot point. Actuating air applies force on one side of the vane. Opposing force can be provided by a spring or an air spring. This type of actuator is not generally installed when it's necessary to develop high forces. Also, friction at the vane seals can cause problems. In this segment, we've covered some of the more frequently used actuators. It's important that you understand how they work and the advantages and disadvantages of each. Additional material can be found in your text. Stop the tape now. Now that you're familiar with some typical control valves and actuators, it's time to take a closer look at some of the parts of a control valve. The control valve trim. Valve trim consists of the removable parts of the valve that come in contact with the process fluid. Let's look at an example. The primary trim in this double-seated globe valve include the plugs, the seats, the valve stem and guides, and the guide bushings. A valve cage would also be considered primary trim. Stuffing box parts, such as the packing follower, springs, and lantern ring, are considered to be secondary trim. Components designed to contain pressure, such as the valve body, bonnet, packing, and flanges, are not considered to be part of the valve trim. There's a wide variety of trim designs available, with each design exhibiting particular properties and characteristics. Some primary considerations when making a selection include capacity and flow characteristics. Both of these are a function of valve trim. To explain how valve trim affects these characteristics, we first need to review some fundamentals of fluid flow. Now, as you may know, in order for fluid flow to occur between these two tanks, a differential pressure must exist and a flow path must exist. With these conditions present, high-pressure fluid flows to the area of lower pressure. The greater the differential pressure, often referred to as the delta P, the higher the flow rate will be. The actual relationship between them is flow rate is proportional to the square root of the delta P. So, for example, changing the differential pressure by a factor of 4 will change flow rate by a factor of 2. Another factor affecting the rate of flow is the flow path itself. The more restrictive a flow path is, the lower the flow rate will be for a given differential pressure. If a flow-restricting device, such as an orifice, is placed in the flow path, flow rate will be a function of the orifice size and the pressure drop across it. Obviously, a larger orifice will allow more flow, and a smaller orifice less. A control valve acts as a variable orifice in a flow stream. The more the valve is open, the more flow it will allow through its orifice. But for a given opening of a control valve and a given pressure drop across it, the flow rate through the valve, that is, the valve capacity, is a function of the design of the valve trim. To allow the liquid flow capacity of different valves and valve trim combinations to be compared, a flow coefficient, C sub V, for each design is experimentally determined. For a given pressure differential and a given liquid, flow rate is proportional to C sub V. A valve with a greater flow coefficient will pass more liquid than one with a lower flow coefficient, assuming all other conditions are the same. A similar factor, the pressure drop ratio factor X sub T, is determined for gases and vapors. Again, flow rate is proportional to X sub T, assuming all other conditions are the same. A valve with a large X sub T will have a higher flow rate than a valve with a small X sub T. In addition to affecting valve capacity for given conditions, trim design will affect how the valve capacity changes as the valve plug moves throughout its travel. The relationship between valve capacity and valve travel is known as the flow characteristic of the valve. Many valves are not linear in nature. Trims are designed or characterized in order to meet the large variety of control application needs. For example, most control loops have some characteristic nonlinearity that can be compensated for with a proper control valve trim selection. Charts like this are used to illustrate the various control valve flow characteristics. The percent of full flow through the valve is plotted against valve stem position. These curves represent typical valve characteristics available from valve manufacturers. They are based on a constant pressure drop across the valve, and as a result are called inherent flow characteristics. These sample curves represent three common flow characteristics. The quick opening characteristic might be provided by a plug with this contour. You can see that it will move out of the valve opening with very little stem travel. A plug with this contour, on the other hand, will provide a linear flow characteristic. Equal increments of valve stem travel will result in equal changes of flow. This shape will result in what is called an equal percentage flow characteristic. Equal increments of valve stem travel will result in equal percentage changes of existing flow. There are many others also. Now, as you can imagine, many of these shapes and styles of trim provide similar flow characteristics, whether they're plugs for single-ported valves or for double-ported valves. Valve cages and seats can also be characterized. Why is such a variety necessary? Because for each application, there are considerations other than flow characteristics, and different trim designs address different concerns to varying degrees. Some of the additional considerations that affect trim design and materials include the need for seat tightness, the need for resistance to corrosion and erosion, the need to minimize fluid forces on the actuator, the need for vibration resistance and valve stability, and the list goes on. Addressing each specific concern has a different effect on trim design and materials. In addition to primary trim, it's important to properly evaluate the type of secondary trim required by the valve application. In the next segment, we'll look at the various secondary trim designs. But for now, stop the tape. As you know, secondary valve trim consists of the stuffing box components. These components prevent leakage of the process fluid past the surface of the moving valve stem. The importance of selecting an appropriate design for a specific application cannot be overemphasized. That's because excessive leakage can result in increased operating costs for a process. Obviously, the primary concerns are personnel, environmental, and equipment hazards, each with their own costs. Additionally, the cost of the wasted process fluid itself is a concern, as well as the possible increase in maintenance time and cost. Unscheduled downtime can also result from excessive leakage. So, with these factors in mind, let's take a look at the design of secondary valve trim for different applications, as well as some of the packing types and materials. Probably the most widely used design is the bolted packing box assembly. Trim components include the packing follower and the lantern ring. The stuffing box is a hollow, cylindrical cavity in the valve bonnet. Ring-shaped packing material is placed in the stuffing box and is compressed to fill the space between the valve stem and stuffing box wall. It provides the actual valve stem seal. As you can see, the packing follower serves to compress the packing and hold it in place. The packing flange serves to adjust the tightness of the packing follower. One common type of packing is a braided material such as this. These materials can be formed as a split ring, allowing for packing replacement without completely disassembling the valve. Also, many of these materials are suitable for use in high-temperature applications. One problem is the friction between these materials and the valve stem. As you may recall, friction between moving parts of a control valve will result in a degradation of control. To help minimize this problem, additives such as Teflon, mica, and graphite are used. Even with these additives, some braided materials require an external source of lubricant. The lantern ring acts as a spacer in the packing that provides for insertion of lubricating grease through a separate packing lubricator. The valve stem is then lubricated as it moves through the lantern ring. When application temperatures are less than 450 degrees, Teflon is often used as the packing material. Its excellent lubricating properties remove the need for an external lubricant. A popular form of this packing is the chevron or V-ring. In addition to providing low friction, it creates an excellent seal. Because of its shape, a pressure increase in this area causes the packing to seal more tightly. In some cases, a spring is used to provide a minimum pressure against the seal. When a spring is used, the packing flange is not adjustable. Also, keep in mind that the spring is in contact with process fluid and must therefore be compatible with the process. A disadvantage of using Teflon rings as a packing material is that it is a preformed ring. Replacement requires considerable valve disassembly. Other packing materials include rings formed of graphite and graphite compounds, and O-rings and V-rings made of materials such as neoprene. All of these materials may be susceptible to some leakage. For applications where leakage is not acceptable, a different seal design must be specified. One such design is the bellows stem seal. An internally pressurized bellows seal is shown here. The flexible metallic bellows is attached to the stem at one end and the valve bonnet at the other. Thus, process fluid is sealed within this area. The material and construction of a bellows limits its use to relatively low-pressure, low-temperature applications. Also, the life cycle of the bellows is unpredictable. Because a failure of the bellows could be catastrophic, this design normally includes a backup packing box. A double packing seal is often used in highly toxic applications. Note that this design has two completely separate, independently compressed packing sets sealing the valve stem. This particular design uses spring-loaded chevron-type packing. In many applications, the space between the sets of packing is vented to a safe disposal point, such as a special waste tank. While leakage may exist, the leakage is not past the valve stem and into the environment. Another approach that can be used to seal this type of valve is to pressurize this space with an inert fluid. A slightly higher pressure than process pressure is used. In this way, any leakage past the valve stem will be inert fluid leaking into the process or atmosphere. So, you see, there are a number of stem seal designs available. When making a selection of seal design and packing material, the value of the process fluid and the hazards of the process fluid must be considered. The compatibility of the process fluid with packing and trim materials must be considered. And the application pressure and temperature must also be considered. Stop the tape now. Up to this point, we've been discussing various control valve and actuator designs. We've discussed some specific types that avoid or minimize potential problems. But because safety is so important in control valve selection, we're going to look at some control valve safety considerations. When selecting a control valve, you should think of it as the last line of defense against a catastrophic failure. You must decide what valve action is needed in case of a loss of control signal or actuating power. Should the valve open? Should the valve shut? Or should the valve remain in its position at the time of the signal loss? Obviously, the action taken depends on the combination of valve style, actuator type, and auxiliary devices. You need to ask, what are the consequences if the preferred action does not occur? Will a hazardous situation be created? Will a relief valve lift? Will product be lost? The answers to questions like these must be your guide in order to make a proper selection. Another consideration is how fluid forces will affect the valve in the event of a mechanical failure. Should fluid forces tend to open the valve? Or should fluid forces tend to shut the valve? As you can see, the concerns will be similar to those for a loss of control signal or actuating power. More information on how the various valve types are affected by fluid forces are included in the text. Water hammer is another effect of fluid forces that must be considered. In some process operations, water hammer can occur if a valve suddenly slams shut. The force generated by the pressure surge can result in piping failure or damage other process equipment. Thermal expansion of liquid in a control valve can also create a safety hazard. There are applications where liquid can be blocked in by a control valve and then heated by an external energy source. This can result in a pressure buildup that could easily cause a valve or piping failure. Pressure relief devices should be used to protect against this type of potential problem. Thermal expansion of valve components may also pose a problem with ball valves. For example, when this type of valve shuts, liquid is trapped in the ball. To prevent damage by thermal expansion of the liquid, the valve must be designed with a suitable vent hole or with a valve seat that relieves internal pressure buildup. Still, other important safety considerations are electrical hazards. Electrical devices such as I to P transducers, positioners, and limit switches are often used with control valves. So it's important to know the electrical classification of the area in which the control valve is to be installed, and that any devices on the control valve comply with all pertinent electrical codes. Improper installations can result in explosion hazards. Another electrical hazard is static electricity. In some applications, it's necessary to install a control valve such that it discharges directly into the vapor space of a tank or vessel. When this occurs, it's possible for the high-velocity jet stream exiting the valve to create a high static charge on the tank nozzle. If the vapor consists of a flammable mixture, a hazardous situation exists. So it's necessary to provide a means of eliminating any accumulation of static charge. Hazards that are peculiar to the specific process must also be considered. For example, characteristics of reactive process fluids require a thorough investigation to determine exactly what hazards exist. Examples of such materials include oxygen, hydrogen sulfide, chlorine, and acetylene. So you can see there are many considerations that must be given to fluids other than its toxicity. It's not possible to list all the potential hazards in this program. You must examine the process to determine what hazards exist and what control valve equipment is most capable of dealing with it. This training program is general in nature. The examples given of equipment operation and applications are for illustration purposes only. Manufacturer's specifications and guidelines, as well as your facility procedures, must be used when sizing or selecting a control valve. Always remember that safety is your responsibility.